Hello everyone, my name is ZHUANG and my matrix number is 231404007 from program UR652100 product design. Today I will be giving a presentation on the MMK36003 computer-aided engineering tool project. The project title is Aerodynamic Analysis of Car Body. First of all, one of the objectives in my project is to analyze the external airflow characteristics around a simplified car body using a CFD. Second is to investigate the effect of difference in air velocities on the aerodynamic drag force and pressure distribution. Third is to study how variations in the front geometry and angle influence flow separation and drag behavior. The fourth is to evaluate the relationship between flow velocity, pressure distribution, and drag coefficients. And the last objective is to visualize airflow behavior using velocity counters, pressure counters, and streamlines for better physical understanding. Next, in introduction, car aerodynamics are important for fuel efficiency, stability, and reducing emission. Thus, testing in wind tunnels is expensive and time-consuming, so that computational fluid dynamics offers a faster and more affordable way to simulate and study airflow around vehicles. This project will focus on the basic car shape and use CFD to understand how speed and the angle between front bumper and windshield affect the air movement and drag. The scope of study will study about variables which is inlet velocity and front angle, and the output is the drag force, pressure distribution, and velocity fields. Now I am presenting about the methodology. This is the flowchart and it will explain at the following slide. The first process is about the geometry or domain construction. This is the specification that I use in my project. Now is about meshing. The beside of the figure is my custom setting for the hex meshing configuration. Next is the slower setting. This is the setting and the reason that I apply in my project. So this is boundary conditions. The setting at boundaries can reverse the slide shows now. But here got some setting have to know is inlet and velocity reference value set as 20 meter per second. And then the turbulence intensity change in 0.005. Besides that, top and rear right must set the flow type in 0 gradient and slip at below. And also at all the turbulence type set as 0 gradient. Lastly, because of the bottom is landing on the base, so the boundaries type must set as wall and the velocity value is 20 meter per second. Then, before run the analysis, must set the samplings to slice such as at the normal need to set 0, 1, 0 and the point is 0, 0, 0. After that, the field must be clicked to observe such as pressure and velocity. Additionally, don't forget set the force at the car body to observe drag force, lift force, and side force. Lastly, set the number of interaction as 200 before run the simulation. Thus, this is the result shown in the same flow of the run the simulation. We will get the velocity counter, pressure counter, force graph, and moment graph. In a grid independent test, I just take 3 different deviations to test, and after that I will calculate the percentage difference to get the best mesh. Hence, after clear the step, now we can run other independent factors such as shown in this slide. Finally, we will get 6 sets of data to analyze or observe. Now, I will presenting the result. First result, I will present about the grid independent test. First, velocity counter show that velocity distribution around the car body using a cross mesh with a cell size of approximate 1.33 mm. The maximum velocity recorded is 33.528 meter per second, which occurs at the junctions between the roof and windshield. The counters appears blurred and it indicating that the mesh resolution is insufficient to capture the sharp velocity gradients accurately, particularly in regions of high curvature. The second velocity distribution is presenting using a medium mesh with a cell size of 1 mm. The maximum velocity increased to 35.529 meters per second located at the same place. The flow details are clearer than the coarse mesh, especially around curved surface, and demonstrating improved resolution and a better capture of the flow acceleration. And the third counter illustrates the velocity distribution with a fine mesh having a cell size of roughly 0.8 mm. The maximum velocity reaches the 38.991 meters per second, and it's providing the sharpest definition of flow acceleration and boundaries layer behavior. Thus, the fine mesh effectively captures the detail for characteristic and it confirms its inadequacy for accurate simulation. Besides that, the table summarizes the key characteristics of three mesh density tests. The coarse mesh consists of 49,000 elements, and the medium mesh consists 89,000 elements, and the fine mesh contains over the 1 million elements. So the fine mesh show that further refinements result in change of less than 1%, thereby confirming grid independence and validating its use for subsequent simulation. Behind that, the line graph illustrates the relationship between the maximum velocity and mesh density. It clearly shows that as the mesh becomes finer, the maximum velocity increases, eventually plating at the fine mesh level. The stabilizations indicate that additional mesh refinement beyond the fine mesh yields negligible change, and is confirming that grid independence have been achieved. The second result will be presented is inlet air velocity. At my left side is render counter at the inlet air speed of 10 meters per second. Show the smooth and attached airflow around the car body, and maximum velocity is 19.491 meters per second located off the road. The acceleration region is relatively small and wake turbulence behind the vehicle is minimal, and it is reflecting stable and low energy flow conditions. At the right side is the pressure counter. The pressure counter's distribution at 10 meters per second inlet velocity show a maximum stagnation pressure of 116.67 Pascal at the front bumper. The pressure gradients along the hood and windshield are marked, and it's corresponding to the low dynamic pressure at the speed. After that, velocity counter at an inlet velocity of 20 meters per second, the flow exhibits the stronger acceleration with the maximum velocity doubling to 38.991 meters per second. The high-speed region of the road expands and the boundaries layers become thinner, and is indicating increased aerodynamic loading and shear force typically of high driving speed. Besides, the pressure counters with the inlet velocity increased to 20 meters per second. The pressure counters reveals a more concentrated high pressure zone at the bumper, and peaking at the 382.19 Pascal. Concurrently, low pressure regions develop above the roof and at the rear, and it contributing to increased lift and drag force. Next, the velocity counter at 30 meters per second demonstrates significant flow acceleration at the inlet speed of 30 meters per second, where the maximum velocity reaches 58.476 meters per second. The roof experiences intense accelerations, and initial signs of frustration appear at the rear, visible as an enlarged wake region, and it highlighting the non-linear relationship between inlet velocity and local flow behavior. At the 30 meters per second, the pressure counter exhibits a sharp peak stagnation pressure of 855.01 Pascal at the front. The strong contrast between high pressure at the front and low pressure on the top and sides indicates a significant pressure differential and leading to evaluate pressure drag. So the third result will be vision is front angle between bumper and windshield. The velocity counter at 20 degrees angle shows a maximum velocity of 34.923 meters per second at the roof apex. The relative step angle causes early airflow separation at the base of the windshield, which disrupts smooth acceleration over the roof and limits peak velocity. At the pressure counters for the 20 degrees angle reveals a maximum stagnation pressure of 386.47 Pascal at the front bumper. The blunter frontal areas present a large surface perpendicular to the floor and is creating a strong height pressure zone. Increasing the angle to 30 degrees, the result in a maximum velocity is 38.991 meters per second. The gentle slope promotes better airflow attached along the hood and windshield, and is leading to smoother and more efficient accelerations over the roof. At the pressure counter, with the angle increased to 30 degrees, the maximum pressure decreased slightly to 382.19 Pascal. The more angle fronts deflect air flows upward more gradually, it reducing the effective frontal area and thus lowering the stagnation pressure. At a 40 degrees angle, the maximum velocity is 39.206 meters per second, only slightly higher than at 30 degrees. This indicates diminishing return as the airflow is already well attached, and further geometry steepening provides minimal additional benefits to velocity. At the pressure counter, the maximum pressure decreased slightly to 379.16 Pascal. It shows a further slightly reduction in maximum pressure as the angle increased to 40 degrees, and is continuing to trend off decreased frontal pressure with a more streamlined shape. Now I will make a summary for maximum velocity and maximum pressure. For the maximum velocity, when verifying the inlet air velocity at a fixed 30 degrees front angle, the maximum velocity showed a near linear increase. It was 9491 meters per second and 10 meters per second, and 38.991 meters per second at 20 meters per second, and 58.476 meters per second at 30 meters per second. This consistent rise highlights the direct relationship between the free stream velocity and localized flow acceleration over the car curved surface. In terms of front angle variation at a constant inlet speed of 20 meters per second, the maximum velocity rose from 34.923 meters per second at 20 degrees to 38.991 meters per second at 30 degrees, and then only slightly to 39.206 meters per second at 40 degrees. This indicates that while a more greater front angle improves airflow attachment and acceleration, the aerodynamic benefit diminished significantly beyond 30 degrees. Regarding the maximum pressure, the result was strongly curved by the inlet air velocity and is displaying a quadratic relationship. At the 30 degrees front angle, the stagnation pressure at the front bumper rose sharply from 116.67 Pascal at the 10 meters per second to 382.19 Pascal at the 20 meters per second, and further to the 855.01 Pascal at the 30 meters per second. These patterns confirm the principle that dynamic pressure is proportional to the square of the velocity, and it making high-speed operation critically important for drag and load management. The effect of the front angle on maximum pressure, while less dramatic, was beneficial. At a fixed inlet speed of 20 meters per second, the maximum pressure decreased gradually from 389.47 Pascal at 20 degrees angle to 382.19 Pascal at 30 degrees and down to the 379.16 Pascal at 40 degrees. This slightly but steadier reduction demonstrates that a more streamlined front end geometry helps mitigate frontal pressure loads, contributing to overall drag reduction. All in all, based on the analysis of the velocity and pressure contours, two key aerodynamics metrics are defined. The maximum velocity refers to the highest speed of the airflow around the cars, which consistently occurs at the transitions between the windshield and the roof. This acceleration is caused by the curvature of the car surface, which compresses the flow. Higher inlet speed or a more streamlined front angle increase this velocity and indicating improved airflow attachment and reduced drag. Conversely, the maximum pressure is the peak static pressure recorded on the car, always located at the stagnation point on the front bumper where incoming airflow decelerates completely. This pressure increase quadratic with higher inlet speed due to the conversion of kinetic energy into pressure. A more stop front geometry can slightly reduce this pressure by making the vehicle more aerodynamic, thereby lowering resistance. Together, these parameters help evaluate how design and operating conditions influence aerodynamics performance. Analysis showed the higher intake velocities and until 30 meters per second result in an almost linear increase in maximum roof velocity, while stagnation pressure and drag increase quadratic consistently with Bernoulli principle. Velocity and pressure contours plot confirm that faster airflow creates a large high-speed region and a stronger pressure zone around the vehicle's front. Besides that, increasing the nose angle from 20 degrees to 40 degrees improve airflow action, reduce the flow aspiration, and lower drags, but these advantages gradually diminish beyond 30 degrees. Numerical comparison show that cost grid underestimate peak velocity by approximately 50%, highlighting the necessity of using fine grids near curved surface. These results are consistent with fluid dynamics principles and previous studies validating the application of CFD in aerodynamics assessment. In conclusion, this CFD study successfully analyzed airflow around a simplified vehicle body, and the key findings include higher intake velocities result in a linear increase in groove speed and quadratic increase pressure and drag. A right angle between 30 degrees and 40 degrees can reduce drag by improving airflow adhesion, but the benefit diminishes beyond 30 degrees. A fine mesh by 0.8 mm ensures numerical accuracy. The result confirms that the aerodynamics load increases the geometric with speed. Therefore, front end has proven to be a cost-effectively aerodynamics design to providing practical insights for developing fuel efficiency vehicles. Thank you.